Hello and welcome to Calculus 2. So this is going to be the second semester of Calculus, where we are going to focus on mainly two topics. Part 1 of the Kalk2, there we go. 1 is going to be integration, and then part 2 is sequences and series and power series, but those are upgrades. We'll see how and why. So these are the two main parts. There is also a third part, which is intro for Calc3. Only 3 sections in chapter 12, where we are going to learn parametric and polar equations and formulas and coordinate system and so on. And that is going to be intro for Calc3. So it's just like an intro little part. So about 90% of the course or 95% of the course will be in these two parts. Now, in order to be successful in Calculus 2, because you probably heard the stories that this class is hell on earth and all of that stuff, the key to success in this course is to be well equipped with the prerequisite knowledge from Calculus 1 and trigonometry. And generally, Trig is the one that creates a lot of fuss over here, because for some of you, Trig was 2 years ago. For some of you, Trig was 3 years ago, and so on. So, and then some students, unfortunately, had access to formula sheet in Precalculus 2, which is something that damages you for life. Because if you don't know basic identities, number of sections in Calc 2 are not going to go well. So this first introductory part here is for us to list exactly the sections from Calc 1 and formulas from Trig that must be known. And I promise you, from that point on, Calc 2 is going to be walk in a park. And your first week of this course, which is up to the next class, should be focusing primarily 90% of your strengths and times, focusing on these prereq sections, practicing them either in a book or MyMathLab, so you guys have the easy time in this course going on. So part 1, integration, we are going to have chapters 6, 7, 8, and 9 in this section. And prereq are sections 4.9, basic integrals, 5.2, which are known as definite integrals. Those are the ones with numbers that you compute a number at the end. And 5.5, U sub. 90 or more % of the problems in Calculus 2 end with U sub, which is 5.5. So technically, if you don't know that section, you are already gone, right? Learn it. If you don't know U substitution 5.5, you have a week to practice it. You can go back on the channel, watch the instruction 1.5 hour video on it, where I do 20 examples or so. You have my MATLAB study plan to go back into 5.5 and practice infinitely many problems, because every time you mess up, the computer will generate a new problem for you and help you solve the problem that you messed up on. So U sub, maybe I should write that in blood here. U sub. Most of chapter 6, most of chapter 8 will be U substitution over and over and over again. So yeah, that's that part. There is also prerequisite of trig in part 1, because we are going to have sections like trigonometric integrals and trigonometric substitution, and also certain integrals that are in other sections, in integration by parts and so on, will also be trig integrals. So there will be about 5 to 10 trig identities, which I'm going to list soon, that you absolutely must know to survive Calc2. Going to part 2 of our course, 100% of the problems will depend on your knowledge ability to take limits. So 100% of problems are take limits, take limits, take limits. Now that is primarily so this is chapters 10 and 11. And the big focus on prereq is limits. So prereq, it's going to be 2.3 limits. This is basic techniques, okay? And then we have 2.5 limits at infinity. And then finally, 4.7, this is the heavy artillery, right? L'Hopital's rule. There will be 0 trig needed in chapter 10, and very little trig needed in chapter 11. Now, as I said, part 3 is to set you up for calc. I can write it in. So, part, there we go. 3, which is chapter 12, that is on parametric polar coordinates, need lots of trig. But that's only three sections, so this is very short. It accounts for maybe 5% of the course. We are going to deal with this in 1 week out of 14 weeks we have. So do not panic about that. And also, if you're not going to Calc 3, it's kind of useless for you, but it is what it is. All right, so let's talk about the important stuff here in terms of prerequisites for the course. Now, derivatives will show up, but they are not going to take the central stage of the course like they did in Calculus 1. About half of your Calc 1, or even more, was derivatives. Calc 2 focuses mainly on integration, and derivatives will play a role. Clearly, they play a role in a U substitution, and I promised you that about 90% of the integration is going to end up being U sub. So they play a big role in a U sub, and then also some of the techniques that you guys will learn in chapter 8, like integration by parts, will also heavily depend on derivatives. But they're not as present as in Calc 1. Trig is the one that most of the time causes the most issues. So let's talk about trig and the things that you absolutely must know to survive this course. We are going to start from ability to set up a triangle with opposite, adjacent, hypotenuse with the angle theta, right, touching, which is why it's called adjacent, right? Hypotenuse in a right triangle is the longest side. We have two legs, which are opposite and adjacent. Opposite is not touching the angle, it's opposite of the angle, and adjacent is touching, right, the angle over there, so adjacent. Sine of angle theta is calculated as the ratio of opposite divided by hypotenuse. Cosine theta is adjacent over hypotenuse, and tangent theta is opposite divided by adjacent side. And from there, we can immediately learn our first trigonometric identity that you absolutely must know, which is that tangent is sine divided by cosine. Now, there are 6 trigonometric functions, and the other 3 are flips of the first 3. Cosecant theta is hypotenuse over opposite, which gives us another formula here that cosecant theta is 1 over sine theta. Secant theta is hypotenuse over adjacent, which gives us a formula secant theta is 1 over cosine theta. Finally, cotangent theta is adjacent over opposite, and that one is going to give us the final identity for these basic ones. Cotangent is cosine theta over sine theta. So this is just the start. These trigonometric functions give us these ratios of length of a side. Now, what are identities that you need to know from Trig to survive Calc2? We're going to start with Pythagorean identity, which has 9 forms. You just need to know one, and then that fans out into the other ones. Sine squared theta plus cosine squared theta is equal to 1. This is the boss equation. Now, if you divide through by cosine squared everywhere, you will get sine squared over cosine squared, and that is tangent squared theta plus cosine squared divided by cosine squared is 1, and then 1 divided by cosine squared is secant squared theta. So just by dividing the first equation, which you must memorize, dividing everywhere by cosine squared, you get the one on the bottom. And we are going to use them all because trig integrals. And if you divide the top equation by sine squared, you get 1 plus cotangent squared theta is equal to cosecant squared theta. Now, I promised 9, I gave you 3. Well, each one of these can be broken into sine squared theta is equal to 1 minus cosine, right? You can flip them with algebra. So there are actually 9 forms, because we will use all of these, actually. So just by flipping them around. But these are the 3 main formulas. The first formula here is the boss, because you can derive everything from this one. And then by dividing by sine squared or cosine squared, you get the ones on the bottom. If I'm writing something in red, which is what I say writing in blood, that means it's the most important stuff you get to see on that lecture, and something that it's absolutely necessary to know to either get through the section or later on to get to something else. The black stuff and the purple stuff and the other colors I bring in because arts. But red is the one that you just make sure you know everything 100% of what's written in red throughout Calc2. The next part here is to talk about 2 formulas that are extremely important. They're called power reducing formulas. Now, you probably encountered this already, You should have in your Calc 1. But these formulas are the only way to integrate sine square and cosine square. If you don't know these formulas, you just can't do those problems at all. And you can't make this stuff up, so, right? So sine squared theta is 1 minus cosine 2 theta divided by 2. And cosine squared theta reduces into 1 plus cosine 2 theta divided by 2. What's left are 2 more formulas and we are done with the trig prereq. Those are sum and difference formulas. They're a little bit lesser importance than these ones, but power reducing are absolutely a must. This one over here says that, you know what, I'm going to put in a parenthesis over here double angle. Because, look at this. If you have sine of u plus v, these are the two values, right? Sine of u plus v, you get sine u cosine v plus cosine u sine v. What is the sine? What is the sine of 2u? Is going to be 2 sine u cosine u. And you get that formula from the one above. Because if you have a sine 2u, then your u plus v is u plus u. And you get sine u cosine u sine u is the same thing, so 2 sine u cosine u. So these formulas are the same, actually, where the one on top is the more general case. That's the way it goes. And we have the one for cosine. We don't have to deal with the tangent. I'm not even going to write it. It's just sine and cosines are the ones that are needed. So cosine of u plus v is going to be cosine of both. So cosine u cosine v minus sine u sine v. So see the sign changed. And now that means that the cosine of 2u is going to be cosine squared u minus sine squared u. And we are done with trig formulas. That's it. These are the trig identities that you must know to survive Calc 2. And this is where your week is going to be at, following the next, right, going up to the next class, which is next Saturday. Now I will immediately, I can't do that because no battery. I will immediately go and discuss the power reducing formula because it's important. Number of times in this class you are going to end up with the integral of sine squared theta d theta or cosine squared theta d theta. This is the one that you really want to star because I even had students memorize the answer to this integral so they don't have to mess. Because it does show up. It's going to show up in trig integration, trig substitution, and then chapter 12. So this integral and the cosine squared are the integrals that pop up. The only way to solve this is to use power reducing formula. So you will rewrite this. Now guys, we are only using Calc 1 here. So it's something from Calc 1. We are rewriting this using the formula as 1 minus cosine 2 theta divided by 2 d theta. From here, we are going to kick 1/2 outside because that is the constant. Limits, derivatives, and integrals kick constants that multiply numbers into a function in front of the whatever operation you have, operator. So we can kick 1/2 in front, and now we have to use parentheses for the rest. The reason why we have to use the parentheses now is because we have a minus sign, and this function here multiplies d theta. D theta is not there for decoration. D theta is the width of the rectangle that you are computing the area for. The function gives you the height, d theta gives you the width. Height times the width gives the area. So this d theta, dx, dt, they are not optional. You have to write them every time because it is times. Now we don't write times. I can write times here with red one time, but we will talk about this when I go to 6.2 after this. We will talk about this again. So you must write this d theta. And that's why we have the parentheses for this notation, because if you don't have the parentheses, that only cosine would be times d theta, but not the 1. You have to have all of this times d theta, which is why we put parentheses there. So if you have multiple terms, and terms are separated by pluses and minuses signs, right? If you have multiple terms, put them all in parentheses, and then d theta at the end. Now, we integrate one by one. We say term-wise. Copy a half, do the parenthesis. Integral of 1 is theta, right? Integral of 1 is x if it's dx. Integral of 1 d theta is theta. And now, integrate cosine. You see, now you are integrating a single cosine. And that is good. That's why we cannot integrate the square. So we use the power reducing formula to get to integrate something that has no square on it. So integral of cosine is positive sine 2 theta divided by 2 because you had the 2 in front. If you remember, and this is where 4.9 kicks in on the list of prereqs. 4.9 teaches you that the integral of cosine ax dx. So you have any number here. In this case, I have 2. You might have 3 or 8. If I have that, the answer is sine ax divided by a plus c, right? That's the answer. So the 4.9 knowledge now kicks in. For us to put that over 2, we close the parenthesis, and then we put plus c. This plus c is not for decoration. It costs -1 points every time you forget it on any of the exams. And then it's going to cost you probably half of the problem in differential equations questions, because you will see how important plus c is when you are in chapter 9. Or when you take the whole course.
Question.
Yes?
Plus c is only for indeterminate?
Yes. Okay. When you have the numbers, plus c cancels. Because it's f of b minus f of a. If each one of them has plus c, then you have a plus c for one, and then minus another c for the other one, they cancel. So plus c always exists. But for definite integrals, we don't write it because it cancels. And that's the next problem. So, great. Now, you may leave the answer this way, or if you want to, you can distribute 1/2. 1/2 will obviously not distribute on plus c because the parentheses are only distributing on the first 2 terms. So you can leave it there, or you can just go and say 1/2 theta minus 1/4 sine 2 theta plus c. I don't care. You can leave it either way. You know who has to care about these things? Computer science people. Do we have computer science in this room? Hi, guys. So 3 of you, right? The reason why you have to care which form is whatever form has less mathematical operations is the one that you have to have. Computers compute things. The less things you have to compute, the faster your software works. It's not just, oh, I'm just going to double the processor and double the RAM. And no. Also optimize the software, which means have all of your mathematical equations in your code to have the least amount of mathematical operations. It's just like, like real life. You go around and the less things you have to do, the less energy and the more time you have. So the same thing for these. So you will actually sit there and you will say 1, 2, 3, 4, 5, 6 operations. 1, 2, 3, 4, 5, 6. Oh, it's the same. So it doesn't matter in this case, right? So that's for computer science. The rest of you, I don't care. Put whatever form you want. Okay, so now to address the plus C business. On our list of part 1 pre-calculus prerequisites, we're not going to do anything on limits today. We're going to do those when we go to the part 2 of the. Today we just integration review. The 5.2 here on the list is for definite integrals. Definite integrals are the ones that have numbers, and they compute a number at the end, and that number might be area under the curve, or might not be area under the curve. Depends on which way the function behaves. So, if we go and say integral 3 to 5 for, let's say, just 2x, because life is like that, dx, we use what we learned as the fundamental theorem of calculus part 1 to solve this problem. Fundamental theorem of calculus part 1 says that the definite integral from a to b of f of x dx is equal to any antiderivative capital F of x computed from a to b, which is capital F of b minus capital F of a. So lowercase f and a capital F are not the same function. Actually, the derivative of big F is a small f. This is why it's called antiderivatives if you go the other way, which is integration. Now, you are supposed to have plus c anytime you integrate. You see, this f of x, the big f of x, will have a plus c to it. And then on the other side over here, you will have the f of b plus c minus the f of a plus c, and you see that the c and c cancel. This is the reason why your definite integrals do not have plus c, because plus c cancels. So we just don't bother writing it at all. You see numbers in limits, that's immediately, you guys just write this and you're done. So now we have to integrate. Integral of 2x is x squared. I'm not going to put plus c because I know it will cancel, and I'm just going to put my limits 3 and 5. This works out to be 25 minus 9 for a total of 16, and we move along with our life. Now, when the function stays above x-axis at all times, definite integral represents area under the curve. Now we can very carefully graph this function, and we can count 16 squares under the curve. This is why this stuff is so awesome. So here's what I'm going to do. I'm going to carefully graph this function. Function is 2x, which means that I have to go 2 units up, 1 unit over. So I have to hit the line in these dots. Obviously, if you're on a lined paper, it's just going to be terrible. So try and get the square paper if you can. So this is the 2x function. By the way, where I come from in the education of the high school, if you don't have a square paper notebook, they kick you out of class. That's the only thing. that's the first reason to kick you out of class. Say, go play ball. School is not for you, because you can't do any of the graphs, and if you can't see things, properly, then what's the point? Here is number 3. Here's number 5. I am going to go up to intersect the function. And we better have exactly 16 squares. Each square is 1 by 1. Our integral is promising us area of 16 under the curve. If I don't have 16 squares, we broke mathematics, we're going home, and we don't have to worry about anything else for the rest of the semester. Fair? Let's count together. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And then the rest is adding up to 16, okay? And the rest will be 16. Now see, what you can do is you can take this triangle here, cut it out, right? And just turn it and fit that in here and fill that area. And then you will have your 15 and 16 easy to see, right? But we do have exactly 16 to count under. So I'm going to put the orange dot here and the orange dot here, signifying that each one of those is one unit when you fill in. There you go, 16, area under the curve. Woohoo! So this is us reviewing some basics, and I'm just going to leave it there. I did ask you to already take a look at as many exercises to refresh your integration tables from 4.9, so you know that the integral, I'll write some of them in blood. Integral of a constant k dx is kx plus c. Integral of x to some n dx is x to the n plus 1 over n plus 1 plus c. These are all 4.9 basic integrals. Oh, by the way, this one covers 3 different types of functions. It covers x, let's say x cubed. It covers cube root of x, because you can write it as x to the 1/3. It's still exponent. And it also covers 1 over x cubed, which is the rational function. So it covers polynomials, it covers radical functions, and rational functions. So it's a really important rule. Covers 3 different types of functions. So you have only constants on top, then you have those 3 types buried in here, and then you have your integral of e to the x dx, which is e to the x plus c. You have your integral over trig dx equals some other trig plus c. Look at that. Integral of 1 over x is important, and you'll be sick of this one. Star it. You'll be sick of this one in Calc2. ln absolute x plus c. That's the one worth discussing. What you do is you forget these absolute values, and then you trigger my inner rage. It's very important to have these absolute values. They're not there for decoration. Here is why. If you observe any of these equations that we write, they have x on the left side and x on the right side of the equation. X can be replaced by any number in the end. Mathematics upgrades. You start by learning to count when you are 3 years old, 2 years old. You learn to count. Then you learn eventually to add numbers, subtract, multiply, blah, blah, blah. You learn later algebra, which introduces x. And x represents any number that you want to plug in. So you learn basic equations and so on. And then you learn calculus later. You see, this x can be 3, can be -7, can be 0, or 1,000,000. And functions have properties so that some values sometimes are excluded from the domain because of the way the function operates. So when I look on the left-hand side, the only value that I am not allowed to use is 0. So if I forget about the integral and dx, just look at 1 over x. Can I plug in 3?
Yes.
I get 1/3, right? Can I plug in -7? Yeah, I get -1 over 7, right? So I can plug any number I can think of except 0. 0 makes this explode. Literally explode. Not figuratively, literally explode. You put 0 there. You don't believe me? Have you ever tried to short circuit the outlet? What happens? Yeah. That's that. Your current in the outlet is given by the equation 110 volt, 118 volts, but 110 volts divided by the resistance. When you take a piece of wire, insulated, so you don't shock yourself, insulated piece of wire, and you stick it into 2 prongs, you get a little explosion. Little explosion, because the fuse popped. Why? Because the little piece of wire that is just a loop, again insulated, is going to go with the resistance down to 0. You are dividing 110 by 0. As soon as you do that, your current is trying to go to infinity. There is a physics formula that says that the current is proportional to temperature. If this is trying to go to infinity, temperature is trying to go to infinity in 0 time. That is how you create explosion in physics, through equations. So anytime you divide by 0,
why is the resistance 0?
Because the wire has, I said going to 0, right? It's not exactly 0, it's going to 0. So when the 2 prongs are open right now, they technically have infinite resistance between them, and there is no current flowing because 110 divided by infinity is 0. If you plug in your cell phone charger, which has the little coil inside to get the voltage from 110 down to 5 volts to charge your phone, you create some current, and that's the 2 amp rating and so on the chargers. So you say, oh, fast charging is 2.1 amps and up, 3.6 amps and so on is the fast charging on the cell phone chargers. So they all have resistance. So you can actually calculate the amount of resistance you have by simply saying, okay, if this is for fast charging 2.1, 110 divided by resistance X. You can calculate what is the resistance necessary. And if you are an electrical engineer, you are calculating these things because you do not want to create chargers and things that explode once you plug them in, right? So for the piece of wire loop that it's, let's say, this big piece of wire with the 2 prongs that it's insulated, if you plug it inside, right? And that's the reason why. So you are not allowed to plug in 0 in the denominator of this function. Now, if you learn enough physics, all of this stuff is very interesting. So we have this graph for 1 over x, which looks like this, and clearly x equals 0 is not producing any y's, which is why the line follows the y-axis, is not producing any y values. Any other point that you pick, and I asked you, can you pick 3? You said yes, and here if I pick a 3, it brings it over here and gives me 1/3 as the answer. If I pick -7, it brings it here, it gives me -1/7 as the y answer. So on the left-hand side of the equation, the only number I'm not allowed to plug in is 0. Now let's say you ignore absolute values here, because you are the person that just likes to annoy people. You know that it annoys me, so you just want to do it. So what happens with your math problem? Well, your ln graph is one-sided. That's what your ln graph is. So your number 3 that works on the left side of the equation also works on the right side of the equation, because 3 will produce ln 3 answer. Now, you don't see any lines on the left side, right? So can you plug in -7? No. You can't plug in -7. So now, on the left side of the equation, -7 is just fine. On the right side of the equation, it's not in a domain. Right? But if you put the absolute values here, it creates another branch on the left side. Absolute value ln x looks like that. Right? I mean, ln absolute value x looks like that. Now, what's the only value you can't use on the right side? It's still 0, right? 0 is still the mean and evil value, but the other values, whether they're positive or negative, work, which is why those absolute values are there. Not there for decoration. Making sure that the domain of the left side of the equation matches the domain of the right side of the equation. So those absolute values must be there. Now, the reason why I say you'll be sick of this is because those integral problems, and this is coming up in chapter 8, integral problems that you were solving as a homework problems in Calc1 will now become pretty much almost every problem in 7.5. Almost every problem in 7.5 will end with, let's say, something like this. Similar, right? Now, this is a Calculus 1 problem, which you solve using U sub. And you will do this so much that you will actually be skipping all of the U sub inside and just providing the answer immediately. You will do so much homework and so many problems, and I'll do also as the introductory, that you will immediately say, oh yeah, that's 3 ln absolute x plus 5 plus c. And you just move along. What are the steps in between? U sub 5.5 is in between. U substitution goes like this. You are looking at this, so I'm just going to cover this because let's say, right, and later when I erase it, it will magically appear. So how do you do this? You say, what I know is that the integral of 1 over x dx is ln absolute x plus c. You also know that you can kick this 3 in front of the integral. You also know that. So the U substitution usually goes as a conversation, with yourself. Those are the first stages. You go, if this was one variable, this problem would match this and it would be easy. So you make it one variable. You say u equals x plus 5. And then du is equal to dx. Now this piece is obtained through differentiation. If you don't know this part, if you don't remember it, here it goes. Du dx is equal to 1, and then you move dx to the other side. That's the way you obtain du equals dx. Because your substitution has to change the function, but it also has to change dx. Because we are changing the domain from x to u, then dx has to change as well. Remember, I told you dx is not there for decoration. It has to be changed also. So now this problem changes into 3 integral 1 over u du. And that is 3 ln absolute u plus c. And then we bring back x instead of u, because the problem was in terms of x, which would give us 3 ln absolute x plus 5 plus c. Now we reveal this one, and ta-da, is the same. I know, magic, right?
It's the same.
So U substitution will be solving about 90% of your integrals in these first 4 chapters, guys. Make sure U sub is good. Let's do one more U sub because we can. First exam is easy in a sense that if it's not U sub, if it's not a basic integral, it's U sub. That's all the choices. You only have 2 choices for the first test. That's it, 2 choices. It's either U sub, basic integral from 4-9, or a U sub. Second exam is going to have 7 choices because you will cover other techniques of integration. But for the first test, if it's not just basic integral, right? How about integral from, let's go with sine to the 6x cosine x dx, because you love trig so much. U sub works by figuring out function derivative pair. Function derivative pair. Anytime you are dealing with a U substitution, you ask yourself, do I have a function with its derivative present? If you don't have the derivative, you can't do du. It's not a U sub problem. So, you look here, you see sine, you see cosine. They are derivatives of each other. Awesome. I can use U sub here. If you just see sine x and then e to the x, that's a spicy problem we're going to call evil problem, and that problem will be dealt in 8.2. Right now, you have 2 functions that are compatible. If you pick sine x for your function, its derivative is cosine x. Woohoo! U equals sine x, which creates u to the 6, because it's sine to the 6. So it's u to the 6. And now, for a du part over here, the du dx is cosine x, and then you move dx to the other side, creating du equals cosine x dx. So this changes just into du. So sine is u, so u to the 6, and the entire string here, cosine x dx is du. Boom. So you transformed this trigonometric integral into a basic joke of a polynomial where you go, integral of this is u to the 7 over 7 plus c. And then you go with the mantra, I don't care about u, I care about the x, which is 1 over 7 sine 7x plus c, and we are done. Now that's the u sub. And now I'm going to ask you to solve sine x to the 6, x to the 5 sine x to the 6 dx. Still has trig in it. Is it the same u sub or a different u sub? Now this is a good opportunity to start talking to the people around you, right? Meet them, work on this together. I can even leave the room. So try this one. Actually, I'm going to. It's warm outside. let's take a look at this together. Do we have a function derivative pair? This is why I drink. It's depressing. Because I ask something and just no one talks back.
Yeah.
It's just, I'm sorry?
X and dx.
Yeah, yes, x to the 6, thank you. All right, so u equals x to the 6, and then du is equal to 6x to the 5 dx. Now, when we compare this x to the 6, right, the whole thing is there. That's great, so it's going to be sine u. Awesome. I don't have that 6, right? I have x to the 5 dx. I need a 6. You fix it. You plug in a 6 and the 1 over 6 in front to counter it. And now you have 6x to the 5 dx for du. And you just replace it like a whole module. So 1 over 6 integral sine u du. Integral of sine is? Negative cosine, yes. So negative 1 over 6 cosine x to the 6 plus c. Ta-da! So I hope you will practice these skills. All of this will pop up, especially one with ln will be annoying a lot, right? It's going to be a lot of that. And we are going to use u sub a lot in chapters 6, 7, and 8, a little bit in 9 as well. So it's very important to review that 5.5 section from your Calculus 1 course. So we'll take about 180 seconds break and then go into the first lesson of Calc2, 6.2 area between two curves.